All right. Okay, so when you talking about the second chapter, measurement techniques, is basically just talking about your quality of measurements. All right, it's meant to describe your quality of measurements when you make some sort of measurements of a physical quantity. Now, when you one way to describe the quality of measurements is by describing the errors that it has. So when you're talking about errors, you have systematic and random errors. Okay. Now, systematic errors will always produce readings that are always either above or below the true value. What would I mean by that is, if you look at the table below here, if let's just say I want to measure the length of a pen like this, okay, let's just say I do repeated measurements for the length of a pen, and the true value is 15.8. Okay, I do a set of repeated measurements. These are the readings that I get. The first set got me this one, second set got me this one, and then the third set got me this one. Now, if you look at this set of readings that you have, we would say that the first set has systematic error, because you see, if the true value is 15.8, all the readings you're getting right now for this one, 15.1, 15.3, 15.8, and 15.6 and 15.5, they are all lower than the true value. And this one here, I will just write it as this. All the values here are lower than the true value. So we would say that this is systematic error. Okay, all the values here are lower than the true value. If you look at the second set of values, 15.9, 16.3, 16.0, 16.5, and 16.2, all of them are higher than the true value of 15.8. So over here, since all the values are higher than your true value, since they're all higher than the true value, we will also say that there's systematic error here. When you're talking about systematic error, all the readings must be either above or either below your true value. Okay, that's the key takeoff point for systematic errors. If you look at the third set of readings, you will see that 15.5, 14.9 are below the true value. But then when you look at 15.9, 16.3, and 16.0, is actually above the true value. So in your case here, the third set of readings here is a mix of values above and below your true value. So this one here cannot be classified as systematic error. For systematic error, you must have all of them either above or either below your true value. If you have a combination of above and below, that one will not be considered as systematic error. It won't be classified as that. Okay, it will be classified as another type of error, which I will talk about later. So here, systematic errors produce readings that are always either above or below the true value. When you have systematic error, it tells you how skewed are your readings from the true reading. Okay, the larger your skewing, meaning to say the larger your readings are from the true value, the larger the systematic error. What we can say about that is that you look at this diagram that you have here, this little line diagram that you have here. Let's just consider that this green dotted line here is your true value. Okay, and whatever readings that you try to make were represented by these orange lines here. Okay, you see your group of readings are over here, right? All of them are below your true value, so it still satisfies the definition of what is systematic error. All of them are below your true value right now. So you see this one here, you see all your values are skewed towards the left or skewed below your true value. Okay, there's a degree of skewing. You can see some sort of offset of your true value from your, sorry, you can see some sort of offset of your readings from your true value. Okay, now if your group of readings here is skewed even more from your true value, is further away from your true value, it could mean something like this. This group of readings could be somewhere around here. So you have an even larger skew. So your skew has increased. Your systematic error here would have deemed to have increased either. The further away you see it from the true value, the more your systematic error. Okay, that's what we mean by the second statement, that the larger your skewing from your true value, the larger your systematic error. Now, systematic errors are caused by poor experimental techniques. All right, they are caused by poor experimental techniques, which would mean with poor experimental techniques is just your experimental fault. Okay, experimental techniques, this one is dependent on your experimental skill. So when you say you have poor experimental techniques, this one is actually caused by the experimental's fault. But that one is not so important here. What you're more interested in is knowing what are the actual causes of the systematic errors. Now, systematic errors are caused by poor experimental techniques, which could be due to the fact that you did not check your zero errors. When we talk about zero error, it is something like this. If let's just say we have an ammeter here. Now, you know an ammeter is used to measure current. Okay. When you're using an ammeter, there's a kind of ammeter called your analog ammeter that looks something like this. All right, there's something like a box looking package, and then there's a readout there where you see that there's a needle. Okay, so when you're talking about zero errors of instrument, it simply means this. If you consider an ammeter, which you know is used to measure current, when there is no current flowing, you expect your needle reading to go back to zero, right? So this one is what we call as having no zero error when no current flows through. It could be that your ammeter was disconnected from your circuit, so there's no current here. By right, you should see that your needle will go back to zero. If you have zero error, what would you see is this. You will actually see that your needle, rather than going back to zero, it stays somewhere around here, not at the zero value. Okay, so in cases like this, we will say that you have zero error. This is what we call as your zero error. What you see is that the needle does not go back to zero when it is supposed to. Okay, zero error is just simply where you're not seeing a zero when you are supposed to. Okay, for example, like now I told you the ammeter, you disconnect it from the circuit, no current flows through. By right, you should see your needle reading going back to zero. But in some cases, it won't go back to zero. It goes at it stops at some non-zero value. So you have zero error here. Your needle doesn't go back to zero when it's supposed to. Okay, this is what zero error is. Then other causes of systematic error could be faulty equipment or unsuitable laboratory conditions. This one is not that important. The more important one is zero error. And then another one one other common cause of systematic error is your parallax error. Now, parallax error causing systematic error is only when the reading is made from the same angle by the same observer. What do I mean by that is this. If you consider when you are doing an experiment in your chemistry lab, doing a titration experiment, you would have probably used a burette before. The burette looks something like this. And then you have something at the bottom here to collect your liquid. So you fill liquid inside the burette, and then after that you will open up the outlet at the bottom so that liquid will go down, will flow down. Okay, so a lot of times when you want to read your volume on the burette, a good practice would be to always read it at the meniscus level. Okay, let me just redraw this properly. Good practice will always be to read it at the meniscus level. This is what you've always learned. You need to read it at the meniscus level, perpendicular to the reading. You always need to read it at the meniscus level. But you see, because your burette is very long and you always need to mount it high above your bench, it is very difficult for you to always read it at the meniscus level when your eye is exactly perpendicular to the liquid level. A lot of times what will happen is that you will actually read it either at an angle above or at an angle below. Now, when you read it at the angle above or below, what will then happen is that you might get a reading something that looks like this. This one here, you get a reading that is above your true value. This one here, you will get a reading that is below your true value, assuming that this one here at the meniscus is your true value itself. Okay, so if you are reading it at an angle, maybe angle theta or angle alpha here, it will cause you to have a reading that is above and below your true value. Okay, so if your measurements are always taken by the same observer at roughly the same angle like the ones here, your readings will always be below your true value. So you will get systematic error here. But if let's just say you have different observer, two different observer, and you are measuring at two different angles, you will get a combination of values that are both above and below your true value. So you will not have systematic error here. Okay, so that's why we told you here, parallax error can cause systematic error, but only if it's made by the same observer at roughly the same angle. Okay, now for systematic errors can be eliminated, but it cannot be reduced. Okay, systematic errors can be eliminated, but cannot be reduced. If you take the average of repeated readings, you will never reduce systematic error. Okay, you will always still get a reading that is below your, or let's just say your readings, like for the case of the readings that you have here, if you take repeated readings and you take the average of the first set of readings, you will still get a reading that's still below your true value. And then you take the average of your repeated readings for the second set, you still get a reading that's above your true value. You won't be able to reduce your systematic error. Okay, so systematic errors cannot be reduced, but it can be eliminated. Now, what do we mean by can be eliminated? Just now I described to you an example of systematic error, which is zero error. When you want to eliminate systematic error caused by zero error, a common thing that you will do is that you will subtract the zero error off from your measured reading. Okay, this is a common thing that your exam questions will test. How do you know how to eliminate the systematic error caused by zero error? Okay, so that is what systematic error is. Then we move on to random errors. The other type of error that you would learn is random errors. Okay, random errors will produce a scatter of readings about a mean value. All right, the mean value itself is not necessarily your true value. If you refer back to the set of readings that you have here, set 1, set 2, and set 3 here, just now I told you that all the readings here were below the true value. This one were all lower. This one was all higher. And then this one was a mix. There's systematic error for both of them, the first two, but there's no systematic error for the last one. Now, looking at all these readings that you have here, you notice that all your readings here have a scatter or range to them. For the first set, you see that there's a scatter in your readings. There's a range to your reading. The same also applies for the second set and third set. So when you see that you have a scatter or range to your readings, this is already telling you that you have random error. So all these three here have random error because there is a scatter or range to the readings. Okay, so I better write it. There is scatter or range to the readings, therefore there is systematic error. Okay, so now the mean, all this scatter here, the scatter you're reading here, or the range of your readings here is actually centered about a mean value. Okay, they are centered about some sort of mean value. The mean value is not necessarily your true value. What I mean by that is that if you try to find the average values for the repeated readings of set 1 and set 2, you can see that the average reading for the first set is 15.1 plus 15.3 plus 14.8 plus 15.6 plus 15 divided by 5, you get 15.2. This is the average for the first set. If you do the same for the second set, you get 16.2 here. You do for the third set, 15.5 plus 16.9, 16.3, 14.9 plus 16 divided by 5, you get 15.7. Now your true value for the length measurement of your pen here, just now I mentioned to you, was 15.8 centimeter. Okay, this one was the true value. So you see now the average or the mean values of your readings, 15.2 is far off from 15.8. 16.2 is also far off from 15.8. Whereas 15.7 is close to your true value. That's what I meant here. Your scatter of readings is centered about a mean value and average value, but that average value is not necessarily your true value. It can be somewhere else. Okay, so in general, when we talk to you about random errors producing scatter readings about a mean value, it will follow that the larger the degree of scattering of your readings, the larger your random error. If you see that your readings are scattered by a larger range, that means your random error is larger. Again, if you refer to the diagram above here, this one was again the true value. Now, the orange lines here are your readings. Okay, you see here, this one is representing your scatter. There's a range in your readings. So this one is considered to be random error. If you look at the second example here, although we write here as systematic error, because you see your readings here, it also has a range. We can also say that there is also random error here. Okay, this particular example here has both systematic error and random error because you see that there's a scatter to your readings. Okay, if somehow your scatter increases, if I refer back to this part here, if somehow your scatter increases, maybe your scatter increases all the way to here where you have your reading stretching all the way to here, this one will say that your scatter has increased, so your random error has increased because the scatter has increased. All right, so that is what we mean by larger the degree of scattering of your readings, the larger your random error. Now, random errors can be caused by fluctuations in external conditions such as temperature or pressure, which is not in your control. In general, random errors is something that is caused by the environment. It's not due to the experimental fault. Systematic errors a lot of times is actually caused by the experimenter. It's the experimental's fault. Okay, but back to what I just said, random error is caused by fluctuations in external conditions such as temperature and pressure. What would I mean by that is this. You see, if the pen that you measured here is made out of metal, all right, you know the metal will expand when temperature increases and will contract when temperature reduces, right? So say for example, when you are taking the measurement for your pen here, you're taking repeated measurements for your pen here, and the temperature somehow fluctuates. If your temperature increases, the metal contracts, your length that you get is going to be larger. On the other hand, if the temperature drops, your metal will contract, the length will drop. Okay, so if temperature is increasing, your metal expands, your length that you obtain is going to be larger. If your temperature drops, your metal will contract, so the length that you get is going to be smaller. So if, let's just say, during the time that you're taking your measurements, the temperature is fluctuating, your length will fluctuate. So when you do your measurements, then you're going to get some fluctuations in your readings too. Therefore, you're going to get a scatter in your readings. That's what we mean by fluctuations in external conditions. Now, another thing that will cause random error is the inability of an observer to measure small intervals or to repeat his actions precisely, which is caused by human reaction time, human limitations such as human reaction time. What we mean by that is this. A lot of times in your paper 3 later on, and even in the previous level, you might have done some experiments that involves timing the oscillation of a pendulum bob. Now, say for example, when you want to find the time for one oscillation of your pendulum bob, you would have to displace your pendulum bob to one side before releasing it so that it makes one oscillation. Okay, so let's just say you want to find the period of oscillation of your pendulum bob. Okay, you will need to displace your pendulum bob to one side, release it so that it goes this side and then goes back this side. That one will constitute one oscillation. So say right now you want to time the oscillation of one pendulum bob. You use a stopwatch. Now, you would start your stopwatch at the moment you release your pendulum bob. Then after that, as it goes to here, stops a bit here, and then goes back to here, when it reaches back the highest point in this oscillation, you will then stop the stopwatch. The time that you have in your stopwatch then is your period. But you see, the thing is that when you do the timing using a stopwatch, how sure are you that you will stop exactly at the highest point of its oscillation here? You might suddenly stop your stopwatch a bit too early or a bit too late. So if you stop your timing a bit too early, a bit too late, that one is due to your inability to repeat your actions precisely. Okay, sorry, this is due to your inability to measure small intervals. Because right now you're trying to press the stopwatch by hand, and by observation using your hand, by observation using your eye, and then coordinating it with your hand movement. So you can, during that small time interval, you cannot do so precisely. You might end up stopping your stopwatch too early or stopping your stopwatch too late. Okay, that's what we mean by inability to measure small intervals. If you were to repeat the same thing again, you were to repeat your experiment to find out the time taken for one oscillation again. When you stop your stopwatch, you won't stop exactly at where you stopped in the previous try. That's what we mean inability to repeat your actions precisely. Each time you repeat the same thing, you're going to end up differently. You're going to end up stopping the stopwatch at a different time. You cannot repeat your actions precisely here. So this is what we mean by that. So your random errors is actually caused by this, because you cannot repeat your actions exactly the same manner each time. Your readings are always going to be slightly different. This is what this is also one of the cause of your random error. Okay. And then random errors can also be caused by parallax errors. All right. But this one is if your readings are made at different angles by different observers. Earlier, I told you that parallax error can cause systematic error, but only if it's made by the same at the same angle by the same observer. All right. Parallax error can also cause random errors. This one is if the measurements are made by different observers at different angles. So just now I give you the example here. You always want to read your liquid. When you want to take volume measurements of the liquid inside your burette, you tend to read it at the meniscus level. All right, that one will give you your true value. But then a lot of times you actually end up looking at it at a certain angle, okay, which in turn gives you a reading that is above or below your true value. So right now, if you have one person reading above at a certain angle and you have one person reading below at a different angle, you're going to end up with readings that are above and below your true values. So that one gives you random error right now. Okay, so bear in mind that parallax error can give you both kinds of errors. Now, random errors is the complete opposite of systematic errors. Random errors can never be eliminated, but it can be reduced. For systematic error, just now we say that it can be eliminated, but cannot be reduced. Random error is the direct opposite. It will never be eliminated, but it can be reduced. You taking the average of repeated readings will actually reduce your random error. Okay, so this is what systematic and random error actually is. Okay, so that one is okay. Then I move on to precision and accuracy. Now, when you're talking about precision and accuracy is also something that is meant to describe the quality of your measurements. Now, when you're talking about precision has two separate meanings. Okay, it depends on the context in which it is asked. Precision, when applied to a measuring instrument, refers to the limit of sensitivity of a given measuring instrument. It is actually talking about the smallest change in measured quantity that can be detected by your instrument. For example, if I use back the example of your pen and I want to measure the length, okay, I want to measure the length of that pen, I could use three different instruments to measure the length. I could use a meter rule, I could use a vernier caliper, or I could use a micrometer screw gauge. Now, for each of these instruments here, the smallest change that they can measure or the precision is different. The meter rule can measure up to plus minus 0.1 centimeter. Vernier caliper can measure up to 0.01 centimeter, whereas micrometer screw gauge can measure 0.001 millimeter, which if changed to centimeter is 0.0001. Out of these three instruments, we will say that the micrometer is actually the most precise because it's detecting the smallest change in length. You see 0.001 is actually the smallest out of these two. So we would say the micrometer is actually the most precise. It's able to detect the smallest change in length. Okay, this is the first definition of precision when applied to an instrument. Now, precision can also be applied to your readings. Okay, when it is applied to your readings in the context of your readings, it refers to the degree of scattering of your readings. Okay. In your case here, your degree of scattering of readings is closely related to your range of measured values. If if your range is larger, your degree of scattering is considered to be larger. All right. So if your degree of scattering is small, we would say that your readings are precise. If your degree of scattering is large, we would say that your readings are imprecise. So take for example the two set of readings that you have here. You want to find out the degree of scattering or the range. Okay, you want to find out the range or the degree of scattering. What you do is that you take the highest value minus the lowest value. That will give you the range or the degree of scattering of your readings. So over here, you take the highest reading, which is 10.6, take the smallest reading, which is 9.8. Your range is 0.8. You repeat this for the second set of readings, you will see that your range is 1.8. So out of these two, you pick the one with the smallest range if you want the more precise reading. Okay, the 0.8 here, the degree of scattering is the least. So we will say that this is more precise. The 1.8 has a larger range, has a larger degree of scattering, so it's actually less precise. Okay, so this is what precision is. It depends on the context in which you are applying it to. Either you're applying it to your instrument or either you're applying it to your readings. If applied to your instrument, it is talking about what's the smallest change that it can measure. If applied to your readings or your measurements, it's talking about your degree of scattering of readings. Now, you may be thinking right now, this definition of precision, isn't it the same as random error? Because random error also talk about degree of scattering of readings. Now, precision is very closely related to random error because they are both talking about degree of scattering of readings, but they are inversely related. What I mean by that is this. You can think of it as this. Precision is inversely proportional to random error. If your precision is higher, you have smaller scatter, your random error is going to be smaller. On the other hand, if your precision is lower, that means you have larger scatter. Wait, let me just repeat what I just said. When we say your precision is higher, that means you have smaller scatter. This in turn means that your random error is small. If we say the converse right now, if we say that your precision is smaller, if your precision is smaller right now, that means you have larger scatter. Your random error is going to be larger. Okay, they are inversely related. Higher precision, lower random error. Lower precision, higher random error. Okay, they share the same meaning, but then they have something like an inverse relation to them. Okay, that's what precision actually is. Now, then we go on to the next one, which is accuracy. Accuracy again has two different definitions. Again, it will depend on the context in which you're applying it to. Now, the first definition of accuracy is something you are most familiar with. It talks to you about how close is your reading to your true value. If let's just say you have some sort of pen whose true value is 5.5 centimeter, you take measurements using a ruler or some other suitable instrument, and you found out that you have 15.3 and 16.5. Now, we will say that 15.3 is actually the more accurate reading. The 16.5 is actually the least accurate. It's actually less accurate because this one, the difference between your reading and the true value is only 0.2. So this one is closer to the true value. The difference between your reading and the true value is only 0.2. So this one is closer to the true value, therefore more accurate. Whereas the second one, 16.5, the difference between that reading and your true value is 1. This one is further from true value, therefore less accurate. Okay, this is what accuracy is. There's also another way to define accuracy. Accuracy refers to the percentage uncertainty of your measured quantity. This is the least common way to define accuracy. Okay, this one is more related to what you will see in paper 3, your practical later on. Okay, so accuracy refers to the percentage uncertainty of a measured quantity. Before I move on, just understand that uncertainty indicates the range where a value, a measured value is likely to lie. Okay. You can just think of uncertainty as something like this first. It indicates the range where a measured value is likely to lie. Okay. And then after that, when we're talking about percentage uncertainty, just take percentage uncertainty as your absolute uncertainty divided by your measured value times 100%. Okay. Just understand these two terms first. Uncertainty is the range where a measured value is likely to lie. Whereas percentage uncertainty is your absolute uncertainty divided by your measured value times 100%. We will talk more about uncertainty in the later part, but just take these two terms as it is first. Okay. Now, percentage uncertainty, yep. Okay.
Yes.
Right. Now, percentage uncertainty will depend on the magnitude of your measured value and the instrument uncertainty used, because you see it's defined like this. Okay. It depends on your uncertainty and your measured value. All right. So say for example, right now you have a book and you want to measure the different lengths of the book, the different dimensions of the book. You want to measure, say, the width, W, the length, L, and then the thickness, T. Okay. So you use a meter rule with an uncertainty of 0.1 centimeter. And then these are the values that you manage to get. So you take this uncertainty, divide by the length, times with 100%, you're going to get your percentage uncertainty as this. Right, 0.7%, 1%, and 2%. Now, what we will tell you is this. The smaller your percentage uncertainty, the higher your accuracy. So all of these three values that you see here, this one is actually the smallest percentage uncertainty. Therefore, it's the most accurate. Whereas 2% is the largest percentage uncertainty. This is the least accurate. Okay? So that is what percentage uncertainty is. How is it related to your accuracy? You want a smaller percentage in the uncertainty of your measurement. So if your uncertainty is lesser, you're obviously going to get a more accurate result. Okay. Then the other thing here that you need to know, this one will be more on your paper 3 later. If you have a given instrument uncertainty, a larger measured dimension will produce higher accuracy. What do I mean by that is this. If you talk about percentage uncertainty being equals to uncertainty over your measured value, maybe I shouldn't do it like this. If I say the percentage uncertainty is equals to your uncertainty over your measured value times 100%, you can see here, if your measured dimensions is larger, this one here is larger, it will cause your percentage uncertainty to drop. It's like maths now. If I tell you A is equals to B, maybe I do this. Maybe I give you this, Y is equals to A over B. All right. If you see that B is increasing, Y would drop. Or A is increasing, that means Y would increase. Because here you see that Y is proportional to A, Y is inversely proportional to B. If B increase, Y drops. If A increase, Y increase. Okay, so right now it's roughly the same format here. Percentage uncertainty is uncertainty over measured value times 100%. Is your measured value large? If you have a certain given instrument uncertainty, this one here being constant, okay, this one is fixed, okay, this one is constant or fixed. If you have a larger measured value, you're going to have a larger percentage. If you have a larger measured value, you're going to have a smaller percentage uncertainty. So you're going to end up with higher accuracy. That's why here we say this. If you have a given instrument uncertainty, a larger measured dimension tends to give you higher accuracy because your percentage uncertainty is smaller. All right. It's inferred from this equation here for percentage uncertainty. All right. Conversely, you can also say this. All right. The converse is also true, where you say that for a given dimension, maybe I just clear everything off. The converse is also true, where you say for a given dimension, a smaller instrument uncertainty produces higher accuracy. This one is you looking at like this. Percentage uncertainty is equals to uncertainty over measured value times 100%. For a given dimension, that means this one is fixed or constant. It doesn't change. So if your uncertainty is smaller, your percentage uncertainty will be smaller. So this one, therefore, more accurate. Okay, this is what we mean. A smaller instrument uncertainty gives you smaller percentage uncertainty, therefore higher accuracy. All right, so it can be inferred either way. All right, so that is definition of accuracy. Okay, now we've gone through systematic and random errors and precision and accuracy. There are some questions that you see that will ask you to identify the amount of errors inside your readings or the amount of precision or accuracy in your readings. Okay, they will give you some graphs, they will give you some diagrams and ask you to identify from that, rather than giving you values like I have in the examples here. Okay, so you need to know how to identify if you are given some sort of diagram or some sort of graphs. Okay, so we start with this one here. Now let's just say right now you have an arrow board where you shoot arrows to it, and then the holes that are made by your arrows here represent your readings. Okay, and then you assume that the middle part here of the arrow board represents your true value. Okay, so by looking at how the readings are on the board or the shots are on the board, you can identify the amount of random and systematic error as well as the precision and accuracy. So what you can see here is this. You first look at, say, the scatter of the readings. You see for the first board and second board, you can see that the scatter is considered to be small. They are close to each other. So the scatter here is small. When the scatter here is small, we can say that the random error, I will just use random error short form. We can say that the random error here is small, okay? because you see the readings are very close to each other. The scatter is small, so the random error is small. And then you look at the third and fourth board, you can see that the readings here are quite far apart. This one here, we will say that the scatter is large, so the random error is large. Okay, so yeah, let me just try to read it all in one shot. Let me just do this again. If you look at the first and second board, you see that the readings are very close to each other. You can say that the precision is, sorry. You can say that the precision is high, the random error is small, okay? So first board, second board, you see the readings are very close to each other. You say that the precision is high, the random error is low. If you look at the third and fourth board, you see that the readings are far apart. That means the precision is low, but the random error is high. Okay, so this is what you can see just by looking at the scatter of the readings. It can already tell you what is the precision as well as the random error. Okay, so this is one part. Next, you look at how close are the readings to your true value, to the middle part of the board. Okay, now before that, you can try to guess out where is the mean value of all your readings here. In your case here, for the first board, your mean reading is probably somewhere in the center of all the readings. There is probably somewhere here. For the second board, your mean value or your average value is probably somewhere here. For your third board, your mean value is probably somewhere here. And then for your fourth board, your mean value probably will be somewhere here. Okay, the green X here represents your mean value. Maybe I should write it here somewhere. This one here represents your mean value. Now, by comparing the mean value location to your true value, the center of the board, you'll be able to see your accuracy. You'll be able to see your systematic error. Okay. Now, if you just look at the first and the third board, you can see that the mean value is very close to the middle of the board itself. So this one, we will say that your skewing, how far your mean value is from the true value, is very little. So we will say that your accuracy is high, your systematic error is low. Okay. Then, if you look at the, let me use a different color. If you look at the second board and the fourth board here, you see that your mean value is situated quite far off from your true value. So this one here, we will say that your skewing is quite high. It's quite offset. It has a very large offset from your true value. So your accuracy is low. Your systematic error is high. Okay, so by looking at it this way, you can see your accuracy and systematic error. All right. So there's a relation here just now that I mentioned before. You can think of precision as being inversely related to random error. You can also think of accuracy as being inversely related to systematic error. What we will say here is this: if your precision increases, your random error drops. If your accuracy increases, your systematic error drops. When precision increases, it means you have smaller scatter. Therefore, your random error decreases. When you say that your accuracy is higher, that means you're closer to true value. Therefore, your systematic error is smaller. Okay, so this is a relation that is useful to know. And that's how you got all these things here. All right. Okay, then there's another second example here for this graph here, for the figure here. Let's just say right now you have a figure that shows you the number of readings and the corresponding lengths that you get. This graph is basically just telling you something like this. Let's say you want to measure the length of a pen, okay? You do repeated measurements for the length, and then you try to produce a graph of it. This graph shows you how many readings corresponded to a particular length for your measurement. Then you get something like this, okay? Now from this graph here, you can see some stuff. You can again see the precision and accuracy and the amount of systematic and random error from that. But first, let's just see this. The red line here represents your true value, okay? And then for the readings that you have here, it follows this little bell curve here. Okay, it follows this little bell curve here that you see. Your mean value is here, this dotted line here. This is your mean value. Okay. Now from here, you'll be able to see a few things, your accuracy as well as your precision. Okay, so right now, let's just say I don't want to talk about systematic error or random error. I just want to talk about the precision and accuracy. If you look at this orange line here, these orange lines here represent your scatter, okay, your range of your readings. You can see that for this one and this one, the scatter is actually quite high, so your precision here is low. This one, the scatter is actually quite high, your precision is low, okay? Whereas if you look at the figure here and here, your scatter is actually quite low, so your precision is high. This one can also be said the same. Your scatter is low, so your precision is high. Okay, that's how you see your precision here. If you want to talk about your accuracy, you see how far away is your mean value from your true value. Okay, so you can see that for this one and this one, the skewing is high, is far apart from each other, so your accuracy is low. This one, the skew is high, your accuracy is low. Whereas for this one and this one, you see that this one, the mean value is very close to your true value, so the skew is very little, your accuracy is high. And then this one, your mean value is at the true value itself, so this one has no skew, your accuracy is actually the highest here. Okay, so that's one way which you can see from this graph. Now, if you are asked to produce if let's just say when you do your experiment in paper 3 and then you plot out a graph, just by looking at the graph that you plot, you will be able to determine your random errors and systematic errors also. What do I mean by that is that if you look at this one here, let's just say I have a relation y is equals to kx. This one, if you know that if you plot a graph of y versus x, you will get a straight line graph that passes through the origin. Okay, right? If let's just say I talk to you about example relation y equals to kx, you plot a graph of y versus x, you should get a straight line graph that passes through the origin. Now, if you try to plot out your data, okay, let's just say right now you measure different values of y for different, wait, let me just rewrite this. Say right now, in an experiment, you measure y for different values of x and plot a graph. Okay, so say you have a relation y equals to kx. In an experiment, you measure y values for different values of x and you plot a graph. If your relationship is valid, it follows something like this. You should get a straight line graph that looks like this. Okay, if your relationship is valid and there are no errors in your measurements, you should get a straight line graph that looks like this. All the points will give you a perfect straight line. If, however, you notice that after you do your measurements and then you try to plot a graph, you get something like this, where your points seem to be scattered about your best fit line. This is indicating to you the presence of random error. Okay, here you see scatter or points about best fit line indicates random error. If you don't see scatter or points of about a line, instead the points describe a nice straight line like this. This one is no random errors whatsoever. Okay, but you see there's a scatter of points about your best fit line. This one is already telling you that you have random error. Okay, now what about systematic errors then? How do you see whether you have systematic error? Now, if your experiment where you measure your values of y for different values of x follows this relation, by right, you should get this graph, the green dotted line here. This is the ideal one. But let's say when you do your measurements and you plot out your actual graph based on your actual values, you get this instead. It doesn't pass through the origin. This one you can see that is clearly systematic error. Because you see all your values are above your true value. So this is systematic error. You might also sometimes get a line that is not above, but rather a line that is below. In cases like this, we will also call this as systematic error. Because all your values, measured values, are below the true value. Okay, so this is how we see whether you have systematic error or not. You would need to see the relation first for that given measurement. If it's telling you you're supposed to get a straight line graph that passes through the origin, that is the ideal one. But if let's say you plot out your graph and you see you're not getting that, is skewed above or below, then you know you have systematic error already. And then additionally, if you see that your points are scattered about your best fit line, that one already tells you you have random error. Okay, so this one here that you see is actually the perfect one. No errors, no scatter of points, no random error, and it passes exactly at the origin. This one, no systematic error. Okay, so that is systematic random error, precision, and accuracy.